Even though the low voltage lights or LED lights in a hot tub do not come into direct contact with water, it is still important to run an insulated ground wire all the way to the main panel and conduit. Here is why. Firstly, safety. An insulated ground wire provides a path for electrical current to flow back to the main panel in the event of a fault, such as a short circuit or an electrical surge. This helps to prevent shocks and potential damage to the hot tub and connected equipment. Secondly, code compliance. Article 680.41 E of the National Electrical Code requires that all grounding conductors for a hot tub be run in conduit. This is to protect the wire from damage and ensure its integrity. Thirdly, electrical isolation. Running the ground wire and conduit helps to maintain electrical isolation between the low voltage lights and the main power supply. This prevents interference from the low voltage lights from affecting the main electrical system of the hot tub. Fourthly, reduce risk of ground faults. An insulated ground wire helps to reduce the risk of ground faults by providing a dedicated path for fault current to return to the main panel. This helps to minimize the chances of stray currents flowing through the water or other unintended paths, which can be hazardous. Grounding is a critical safety measure in electrical systems. It provides a low impedance path for fault current to flow back to the source, which helps to quickly trip a circuit breaker or fuse and to energize the circuit in the event of a fault. This reduces the risk of electrical shock and fire. The ground wire is typically connected to the metal enclosures of electrical equipment and appliances, as well as to the grounding electrode system of the building. The grounding electrode system is a network of conductors that are buried in the earth and connected to the building's electrical system. This system provides a connection to the earth, which helps to dissipate fault current and prevent voltage buildup. When a fault occurs, the fault current flows through the ground wire back to the source. This current causes a voltage drop across the impedance of the ground wire. The voltage drop is proportional to the magnitude of the fault current and the impedance of the ground wire. The impedance of the ground wire should be as low as possible to minimize the voltage drop and ensure that the circuit breaker or fuse trips quickly. The National Electrical Code provides specific requirements for the size and installation of ground wires. These requirements are designed to ensure that the ground wire can safely carry the maximum fault current that is likely to occur. The code also requires that ground wires be protected from physical damage and corrosion. Grounding systems are essential for protecting people and equipment from electrical hazards. By providing a low impedance path for fault current to flow back to the source, grounding systems help to quickly energize circuits in the event of a fault and reduce the risk of electrical shock and fire. Conduit provides physical protection for electrical wiring. It is a rigid or flexible tube that is used to enclose and protect electrical conductors. Conduit is typically made of metal or plastic and is available in a variety of sizes and types. The National Electrical Code provides specific requirements for the installation of conduit. These requirements are designed to ensure that the conduit is properly supported and protected from damage. The code also specifies the types of conduit that are permitted for use in different applications. Conduit is an important part of electrical systems. By providing physical protection for electrical wiring, conduit helps to prevent damage and ensure the safety of the electrical system. Electrical isolation is the separation of electrical circuits or equipment to prevent the flow of current between them. This is important for safety and to prevent interference between circuits. There are several ways to achieve electrical isolation. Firstly, physical separation. This involves physically separating the circuits or equipment so that there is no direct electrical connection between them. This can be done by using barriers, enclosures, or other physical means. Secondly, insulation. Insulation is a non-conductive material that is used to cover electrical conductors. This prevents current from flowing from the conductor to other objects or circuits. Thirdly, transformers. Transformers are used to transfer electrical energy from one circuit to another without a direct electrical connection. This provides electrical isolation between the two circuits. Fourthly, optoisolators. Optoisolators are electronic components that use light to transfer signals between circuits. This provides electrical isolation between the two circuits. Electrical isolation is important for safety and to prevent interference between circuits. By using one or more of the methods described above, it is possible to achieve electrical isolation and ensure the safe and reliable operation of electrical systems. Ground faults occur when electrical current flows to ground through an unintended path. This can happen when insulation on a wire fails or when a conductive object comes into contact with a live wire. Ground faults can be dangerous because they can cause electrical shock or fire. There are several ways to protect against ground faults. Firstly, grounding. Grounding provides a low impedance path for fault current to flow back to the source. This helps to quickly trip a circuit breaker or fuse and energize the circuit in the event of a ground fault. Secondly, ground fault circuit interrupters, known as GFCIs. GFCIs are devices that monitor the current flowing in a circuit. If the GFCI detects a ground fault, it will quickly trip the circuit breaker and energize the circuit. Thirdly, insulation. Insulation is a non-conductive material that is used to cover electrical conductors. This prevents current from flowing to ground in the event of a fault. Fourthly, proper wiring practices. Proper wiring practices can help to prevent ground faults by ensuring that all wires are properly insulated and connected. Ground fault protection is an important safety measure that can help to prevent electrical shock and fire. By using one or more of the methods described above, it is possible to protect against ground faults and ensure the safe operation of electrical systems. Article 680 of the National Electrical Code covers the installation of electrical wiring and equipment for swimming pools, hot tubs, spas, and other similar installations. This article provides specific requirements for grounding, bonding, wiring methods, and equipment location to ensure the safety of people using these facilities. Some of the key requirements of Article 680 include: firstly, grounding. All metal parts of the pool, hot tub, or spa, including the reinforcing steel in the concrete shell, must be bonded together and connected to a grounding electrode system. This helps to prevent voltage buildup and reduce the risk of electrical shock. Secondly, bonding. All metal parts of the electrical equipment associated with the pool, hot tub, or spa, such as pumps, heaters, and lights, must be bonded together and connected to the grounding system. This helps to ensure that all metal parts are at the same electrical potential. Thirdly, wiring methods. Wiring methods for pools, hot tubs, and spas must be suitable for wet locations and must be protected from physical damage. The code also specifies the types of wiring methods that are permitted for use in different areas of the pool, hot tub, or spa. Fourthly, equipment location. Electrical equipment must be located at a safe distance from the pool, hot tub, or spa to prevent accidental contact with water. The code also specifies the minimum clearances for electrical equipment from the water's edge. Article 680 is an important part of the National Electrical Code that helps to ensure the safety of people using swimming pools, hot tubs, and spas. By following the requirements of this article, it is possible to reduce the risk of electrical shock and other hazards. Here are some additional details on the specific requirements of Article 680.41. E. Regarding the wiring of hot tubs. 680.41. E requires that all metal parts of the hot tub, including the metal shell, the metal frame, and any metal piping, must be bonded together with a solid copper bonding conductor not smaller than 8 AWG. This bonding conductor must be connected to the equipment grounding conductor for the circuit that supplies power to the hot tub. The equipment grounding conductor must be sized in accordance with Table 250.122 of the National Electrical Code, and it must be run in the same raceway as the circuit conductors. The bonding conductor and the equipment grounding conductor must be installed in a manner that provides a permanent and effective ground fault current path. This means that the conductors must be securely connected to the metal parts of the hot tub and to the grounding electrode system. The grounding electrode system must consist of one or more grounding electrodes that are installed in accordance with Article 250 of the National Electrical Code. The grounding electrodes must be located as close as practicable to the hot tub and they must be connected to the bonding conductor and the equipment grounding conductor with a solid copper conductor not smaller than 6 AWG. In addition to the requirements for bonding and grounding, Article 680.41 E also includes requirements for the wiring methods that are permitted for use with hot tubs. The wiring methods must be suitable for wet locations, and they must be protected from physical damage. The code also specifies the types of wiring methods that are permitted for use in different areas of the hot tub. By following the requirements of Article 680.41 E, it is possible to ensure that hot tubs are installed in a safe and compliant manner. The National Electrical Code, or NEC, is a widely adopted code for the safe installation of electrical wiring and equipment in the United States. It is published by the National Fire Protection Association (NFPA) and is updated every 3 years. The NEC is not a law itself, but it is often adopted by state and local jurisdictions as part of their building codes. The NEC covers a wide range of electrical topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is divided into chapters and articles, each covering a specific area of electrical work. The NEC is intended to protect people and property from electrical hazards. It sets minimum safety standards for the installation of electrical wiring and equipment. Compliance with the NEC is essential for ensuring the safety of electrical systems. The NEC is used by electricians, electrical inspectors, and other professionals involved in the electrical industry. It is also used by homeowners and business owners who want to ensure that their electrical systems are safe. The NEC is a complex document, but it is essential for anyone who works with electricity. By understanding the requirements of the NEC, it is possible to install and maintain electrical systems in a safe and compliant manner. Here are some of the key areas covered by the National Electrical Code. Firstly, wiring methods. The NEC specifies the types of wiring methods that are permitted for use in different applications. It also includes requirements for the size and type of conductors, as well as the installation of raceways and boxes. Secondly, overcurrent protection. The NEC requires that all electrical circuits be protected by overcurrent devices, such as circuit breakers and fuses. These devices are designed to protect the wiring and equipment from damage in the event of a short circuit or overload. Thirdly, grounding. The NEC provides specific requirements for grounding electrical systems. Grounding helps to protect people and equipment from electrical shock by providing a low impedance path for fault current to flow back to the source. Fourthly, equipment installation. The NEC includes requirements for the installation of electrical equipment such as lighting fixtures, appliances, and motors. These requirements are designed to ensure that the equipment is installed in a safe and compliant manner. The NEC is constantly being updated to reflect changes in technology and to address new safety concerns. It is important to stay up to date on the latest edition of the NEC to ensure that your electrical systems are safe and compliant. In addition to the NEC, there are also a number of other standards and codes that may apply to electrical installations. These include standards from organizations such as the Institute of Electrical and Electronics Engineers (IEE) and the American National Standards Institute (ANSI). It is important to be aware of all of the applicable standards and codes when working with electricity. Electrical safety is a serious matter. By following the requirements of the NEC and other applicable standards, it is possible to reduce the risk of electrical shock and fire. Always consult with a qualified electrician if you have any questions about electrical safety. Understanding the NEC requirements for hot tubs is crucial for ensuring safety and code compliance. Even though low-voltage lights may seem harmless, the potential for electrical faults and the need for a clear path to ground necessitate the use of insulated ground wires run in conduit. This approach provides a safer environment for users and protects the equipment from damage. The NEC detailed guidelines, particularly in Article 680, aim to mitigate risks associated with electrical systems in and around water. Following these regulations ensures a properly grounded and electrically isolated hot tub, reducing the likelihood of ground faults and electrical hazards. Therefore, adhere to the code specifications for grounding and wiring to guarantee the hot tub's safe and reliable operation.